So hello everyone, today we're going to talk about cratering. So we're going to look at the morphology of craters, describe the phases of crater formation, and explain a little bit into crater dating. So what cratering is, it's our final surface process. It is an event where an object hits another object and leaves behind an impact crater. Here's a lovely example of a crater on many craters, including one big one on Mimas, a moon of Saturn. Now, for many objects in the solar system, this is the dominant surface feature. Basically, if you are too small to have anything else, your dominant surface feature will be craters. This extends down to just the smallest of asteroids, where essentially they are small rubble piles. They don't hold themselves together very well. The craters don't tend to form very efficiently and get covered up pretty quickly. Now, typical impact velocities are going to be on the order of the local orbital speed. So that's about 10 to 70 kilometers per second. You know, they're also going to get a boost if you are a larger planet. Anything that hits you, by definition, has to be moving at least your escape speed. Because remember, that's the speed that something would need to go to infinity. So conversely, if you take something at infinite distance at zero velocity and give it a tiny, tiny nudge towards the planet, it's going to hit the surface at the surface escape speed. So, all right, let's look at crater morphology. And you might think, well, it's just a big hole. That's not strictly true. Crater morphology varies based on the energy of the impact and a little bit based on the subsurface. Now, the rule of thumb is that a crater is about 10 times the size of what made it. We're going to look at a little more detailed relationship, but it's a good, order of magnitude estimate. And that reason the crater is so big is basically because this thing is traveling at orbital velocities, so you're going to get a big old explosion. That is what carves out the crater. It is less about the physical object punching a hole and more about a giant explosion happening. So simple craters are bowl shape. Now on the moon, this means something like a 12-kilometer crater. Now this scales inversely with G. The bigger gravity is on a planet, the more the planet kind of pulls itself together, and the more you get kind of a rebound and reaction, so you get something more than a bowl crater. So this crater on Mars is about 1.5 kilometers across. You have meteor crater, which is on Earth, which is about a kilometer across. And for the most part, these are nice, simple bowl-shaped craters. Now, as they get bigger, what tends to happen is you have the crater flattens out on the bottom. You don't have that nice bowl. You have a clear pit, with a steep rim, but the bottom is flat. And often there's something in the center. So like, for instance, you have a central peak. And in even larger craters, you can have rings and more complex morphology. Picture is an example of Tycho crater on the moon. You can see there's a nice peak in the center. The crater's about 85 kilometers across, so it's much bigger than the ones we were looking at. Now, this one is MSQ crater. I'm probably pronouncing it wrong. On Mercury, you can see that it is a bit bigger than the one on Tycho, and Mercury also has slightly stronger gravity than the moon because of its giant core. And you can see that's clearly a peak ring. And the interesting thing is we don't see a lot of the complex craters on icy bodies because something of the material properties is playing in the fact. And you can get even bigger craters, a multi-ring basin. So this is Mare Orientale, which is a lava sea on the moon, but it was originally carved out by a crater, and then the lava just filled in the crater sometime later. And you can see in the picture, it looks kind of bullseye-ish. The main clue of crater morphology here is that it's very round and concentric. See, there's a bunch of little small craters on top of it. And we're missing the bottom because basically that's where the lava lake filled in. But you can see You get all these complicated features. So let's talk a little bit about crater formation. So craters go through 3 stages in formation. And this might look a little bit like 5 stages, but first you have contact and compression. This is the physical act of something hitting your planet. The impact happens and you get a shock wave, and it compresses the material all around the impact site traveling outward. And then the material decompresses. And what happens when you compress a lot of rock? It heats up, and then when it decompresses, it now has room to expand and it can liquefy or vaporize. So this then creates a step of excavation. The vaporized rock basically can expand up and out and carve out what we call the transient crater, the first crater. And then once you have that crater, it's just carved out by the shock wave. It might not be stable versus gravity. You might get slumping and other modification and other geological processes. That's the third step, collapse and modification. Gravity and other stuff is now able to fill the thing in after excavation happens really quickly. So basically what happens is you get a big explosion, it carves out a temporary hole, and then everything kind of slumps back into some kind of equilibrium. So because typical impact speeds are hypersonic, they're faster than the sound speed through rock. When the impactor hits the planet and suddenly comes to a stop, the pressure wave it creates is hypersonic. It's faster than the sound speed. It's a shock wave. Now, after a shock wave always comes what's called a rarefaction wave. It's kind of, shock wave is the compression part, the rarefaction is the release. And that's generated when since the shock wave is also traveling through our impactor, that's generated when it hits the end. Now, the pressures in this are really large. They're megabars. So there's this, we talked about how impacts can create metamorphic rocks due to the high pressures, and that's why. And the rarefaction wave often, vaporizes the rock around the impactor, which is going to carve out our transient crater. Now, as this wave travels outward, we're losing energy just like any other wave. We're losing, and it's also, the energy is going into heating the rock, so we're losing energy that way. So eventually it becomes subsonic, and then we stop vaporizing the rock. We still can move it around, and eventually it dissipates. Now, one of the interesting things is if you look at the picture, we're in the excavation stage now. We're carving out our crater. Is near the edge of the crater, the outer layers are starting, once they finish, once we're past the vaporization part, the outer layers are getting pushed outside and launched upward. So we get what's called inverted stratigraphy. Stratigraphy is the study of layers of rock. And inverted stratigraphy is when the layers are in the opposite order. Normally you have the layers that are most recent on the top and the layers that are oldest on the bottom, but the crater is flipping all those layers over. So then you're going to get the ones on the most recent that are kind of on the bottom, or at least kind of in a sandwich. And this also launches a bunch of ejecta. So what happens is you can get what's called secondary craters. Basically, smaller craters that were launched because our primary crater launched some debris and they basically traveled a parabolic path. They tend to be smaller both because the debris is smaller and because they're moving at slower speed. If they were moving at escape velocity, they would leave. And we'd have another Martian meteorite or lunar meteorite. Now, so the picture I just pulled up kind of shows where we're, what we're looking at when something hits and we excavate a crater. We vaporize a bunch of rock, and then we don't quite get it hot enough to vaporize it, so we melt it. And then we get metamorphic rock that's under enough pressure that it doesn't melt, but it does change crystal structures, becomes a different kind of rock. And we also get a lot of fracturing and brecciation. We get those impact breccias. So here's an example of it in that inverted stratigraphy. is you get kind of a sandwich with the whatever the surface layer was in the middle, and then on the top of the sandwich you have them in the going with the oldest on top. The bottom of the sandwich you have them normal. This is from meteor crater, looking at the sediments from there. All right, so that melted and excavated rock forms what's called an ejecta curtain. And you also end up with what's called an ejecta blanket when that curtain kind of falls down. So if we look at a bunch of those craters, like this one I showed you earlier on Mars, we can tell it's a relatively recent crater because we can see that change in texture around it. That is the ejecta blanket. All of that kind of circular stuff around the crater was stuff carved out from the impact that basically flew up in the air and then landed. Now, the interesting thing is that this is kind of a free sample to carve a giant hole in the planet. We can't send a kilometer-sized asteroid at Mars to see what happens, and even if we could, we probably shouldn't. But the simple natural processes send them at them reasonably often from a geology point of view, and that means we get a free sample of what the top few kilometers of Mars look like. And we get these kind of weird flow features, or some of that could have been due to lava, melted rock. But based on the energy, the size, the energy of the rock, or the energy of the impactor, and where these happened, we think this is water or carbon dioxide under where these things hit, and that helped fluidize the ejecta. It was kind of a slushy water, carbon dioxide, rock mixture, and it made look a lot more like, you dropped it into something wet. And you can kind of see the comparison. There's the moon, a bunch of craters from the moon. They're reasonably big, 5 to 10 kilometers across. That last one, Tooting, appears to be maybe 20 or 30 kilometers. And then here's a more recent crater on the moon, Tycho. You could see that its ejecta is a lot more kind of powder. Powdery, I guess, would be the kind of word I'd use. Seems a lot more particulate, though those particles, since on the scale, you can see this is a full moon. The particles would be more like, boulders, large rocks. Now, another thing you can notice on Tycho is that we can see those rays. We can see long streaks coming from the crater, as well as just the general ejecta blanket. In fact, this was really useful. Apollo astronauts, one of their landing sites was near one of those rays, so they brought back some rocks from Tycho. So we know a lot about that particular impact site, even though we didn't visit it. And as I mentioned, the larger pieces can form what are called secondary craters. They can form craters basically not from something actually hitting the moon, but from something hitting the moon and launching moon rocks, which then are moving fast enough that when they fall down, they make a crater. You can see some of the ones from Copernicus. And this is one thing we study a lot because, as we're going to talk about, craters are really important for learning about the history of the solar system. All right, so excavation ends when we have this transitory crater. Now, here's some scaling relationships. We're going to look more at this later in class. That the diameter of the crater is based on the impact energy divided by g to the 1/4. Now, that's the nice, simple, quick and dirty method. Now, remember, impact energy is going to be mv squared. So we have mass to the impactor mass to the 1/4, impactor velocity to the 1/2. And roughly speaking, for a crater, the height of the rim, that's how much ejecta and inverted stratigraphy is piled up above the original ground level, is about 4/100ths so that'd be 1/25th of the diameter of the crater. And the rough estimate of the crater depth is about 1/5 the diameter. These are all empirical relationships. These are based on observing lots and lots of craters. This is not based on physics, because the physics is really complicated. We often do models. In fact, let's look at some models. So this is the crater. It's on the moon. You can see the impact, or it's much smaller than 1 kilometer. Here's our scale. We hit play. See it carve out our, we don't really see the first 2 stages, but we can see it excavating and see our lovely ejecta blanket. And you can see it kind of folding over, making inverted stratigraphy. And you can see this is a nice simple crater. We're getting a little bit of slumping, a little bit of that collapse and modification, but for the most part, we ended up with something that was, very nicely bowl-shaped. Also notice the time scale. This is over a few minutes. So let's look at a more complicated crater. This is on Earth instead of the moon. And again, we have a similar scale as the previous one, but Earth has a lot more gravity, so we get that transition from simple to complex much earlier. So let's hit play. So there we get a nice crater, carved out our transient crater excavation. We've got our ejecta, curtain, yeah. And notice how the ground is rebounding a lot here. As well as stuff slipping down the sides, producing, an uplifted center. The model's having a little trouble of dealing with some of the rock, but producing an uplifted center and kind of sloped edges rather than, a nice simple bowl. So it's a little bit shallower than our moon crater in terms of, depth to diameter ratio. All right, let's switch to a much bigger one. So now we're going to do a really big one. Let's look at Mare Orientale, the one that we were looking at as a multi-ring structure. Now notice the scale. We've jumped up to 500 kilometers across and 200 kilometers deep. You could even see that the model includes a crust and a mantle. Let's hit play. Again, we get our transient crater. This time there's a giant amount of rebound. This rock, the model isn't clear on whether this rock is solid or liquid, but it's definitely fills in that giant hole, leaving something that's really relatively shallow compared to its distance. You can see the rock from it's disturbed all, for 1,000 kilometers across this box, and including having some of the deeper rocks now at the surface, as well as some of the inverted stratigraphy, but the depth is really shallow compared to the diameter because basically it could not sustain depths more than, a few kilometers deep. Finally, let's look at one more. This one's going to be in between the first 2, which is just because it's a simulation of a rather famous impactor. So this is Chicxulub. So this is Chicxulub crater. So this is the Chicxulub impactor. This is the famous one that killed the dinosaurs. So let's hit play. And again, we have a model that shows different layers of the Earth. We have brown for crust, gray for mantle. And again, we get a lovely rebound. This is going to make a nice big complex multi-ring crater. This one's much smaller than Orientale, only maybe 100 kilometers in radius, so only about 200, so maybe a fifth the size. And notice again, we get some uplift from the mantle. We bring up rocks from very deep in the Earth's crust, or much deeper in the Earth or the moon's crust, as well as getting stuff burying some of the crust rocks. So there's all kinds of interesting structures that our model suggests we should find. And again, we end up with a very shallow crater because the size of the diameter of the crater can't sustain the depth of the transitory one. If you look at it again, you can see it gets down to maybe a 30-kilometer deep transitory crater, like something that looks very bowl-shaped. But watching it again, but that can't be sustained, stably. So the rock rebounds and we fill it in and get a much shallower permanent crater along with those nice Terrence built. And there's still going to be more geologic change after this. We only looked at it for like 8 minutes. But this kind of captures the transition from impact to temporary crater to temporary crater kind of filled in. So we're looking at that complex stage, reshaping the crater. Simple craters, again, they don't have much of this. They have a little bit of slumping. Complicated craters, as we saw, they make those they often have something going on at their peaks, their peak or the peak ring. If we went back to some of those pictures, you could see that a lot of them had something at where the impactor happened due to that rebound. And you also get some of those things that you don't get the nice sharp drop. You get terraces and other features, those multi-rings like at Mare Orientale. Now, for crater sizes, on Earth and Venus, we don't get small craters because on Earth and Venus, we have thick atmospheres. Mars's atmosphere is pretty thin, so while like really small stuff like dust grains can be stopped, big, even relatively modestly sized stuff will make a crater on Mars. On Earth, anything smaller than maybe 1 kilometer will break up in the atmosphere. So this is an example of the Tunguska region, which in 1908, on Earth, where in 1908, an impact happened, or rather an impactor came in, but exploded in our atmosphere, because when you're moving at 30 kilometers per second, air is still an effective barrier to you. It is still putting you under a lot of stress. And if you are not a particularly strong body, you explode. And you create some of the same features of an impact, but usually not as deep, because you're carving it into mostly the air, and the air can just flow back. So on Tunguska, if an expedition was sent out a few decades later to figure out what the heck just happened, and even then they could see the damage from trees over kilometers. They could see that this explosion, the shock wave in the air, knocked down all the trees in a that clearly pointed out where the explosion was. And the ones near the center were still standing, but they were completely denuded of all their branches. And we can also see an example of a shock wave if you look up videos of the Chelyabinsk impactor from some years ago. But we see this on Earth and Venus, that we don't see very many small craters because they essentially form these transient features by exploding in the atmosphere. On Earth, we can witness this. On Venus, we can't. That's the main difference. All right, so let's look at crater density now. So everything in the solar system is constantly getting hit. Again, Earth and Venus, we tend to have our stuff hit, break up in the atmosphere. But we notice that even on an airless body on the moon, nothing stops cratering on the moon. Some regions are full of craters, some regions are not. So here's a picture of the moon. You can see in the center, there's lots of craters. But if we look at this region, Mare Imbrium, the crater density is much less in here. There's fewer craters per square kilometer. And that's important because, again, we're assuming everything gets hit by the craters, and other surface processes, tectonics, erosion, volcanism, whatever else you can imagine, destroy craters, or they modify craters. Therefore, if we count the number of craters and we count their sizes, we can use it to estimate when the last time a major tectonic or volcanic event happened, or how fast erosion works on this planet or in this region of the planet. Now, we include both the sizes and the numbers because there's a lot more small stuff than big stuff in the solar system. So small craters can often give us a more accurate account if we're not Earth and Venus, where the small stuff doesn't exist. So the more craters of any given size, the longer it's been since that surface has been covered in lava or, resculpted by tectonics or eroded seriously. Now, what can happen is even on the moon, you can reach a point where we call it saturation, where basically any crater will erase, on average, will erase one crater of the same size. So basically what happens is at that point, you can't tell how old it is beyond it's reached the saturation age. And the other thing you have to be careful of small craters is those secondary craters. You have to try to get rid of those. And a lot of work has gone into, for instance, isolating how to tell a secondary crater and how many secondary craters we expect. So we use this for a relative aging method. If we want to figure out how old something is relative to some other place on that body, we count the craters. We measure, okay, here's the sizes, and then here's how many there are per patch of ground. So what's their density? So this works fine for relative ages. This is fine to compare places on the same planet. And you can kind of fudge it a bit to do different planets. The impacting rate isn't the same everywhere. For instance, Mars gets hit a lot more than we do because Mars is closer to the asteroid belt. But so we really want some absolute method of aging, even if it's not as accurate as we'd want. And there, the key is the moon. Our moon is covered in craters. That's pretty visible. The moon is the only large body in the solar system besides the Earth, which is kind of bad for this because we have lots of other stuff covering our craters. But the moon is the only body other than the Earth where we have a lot of rocks from it, and we know exactly where we picked those rocks up. So we can match how many craters were in this square kilometer of rocks the Apollo astronauts landed in, and they bring us back a rock, and we can date it. So here's kind of a neat timeline. So the bottom this is from a matcha cup. The bottom has the absolute age in giga years, billions of years. And then the horizontal axis has the number of craters that are larger than 1 kilometer and per kilometer squared. And it's multiplied by 10 to the negative 4 because large craters are rare. And each of these little data points is telling us this is the region that our sample came from. And then here's our error in the age of the sample, and here's our error based on basically this region has a finite size and there's some random chance in it. So you can see we have a lot of Apollo samples, 14, 11, 17, 15. We also have samples from the Luna mission, the Russian Luna missions, which were robotic. So I have 16 and 24. Again, people tried to sort out things like, which rocks were probably representative of the plate of where we're going in place versus which rocks came from another place via a cratering process. Like that's why you have a Mare Orientale. You can see you get them that in the past, regions below about maybe 3.25 billion years have a lot more craters than even a region that's only 3 billion years old. So the cratering rate is not constant. It seems to be much higher earlier on in the solar system, which is a useful thing to know if we're trying to figure out relative ages. And we can also do this with smaller craters if we want to sample the more recent history. Smaller craters would be saturated at these timescales, but if we were interested in more recent history than 3 billion years ago, we would look at those because terrains that are younger wouldn't be saturated. So, all right, if we have these samples from the moon, we can come up with a time function. This is how to convert from number of impacts per kilometer of a given size to an age. So now we can figure out the estimated age of any part of the moon. And it also gives us kind of a general trend. We would be kind of weirded out. It's not impossible, but it would be a little weird if the impact rate on the moon had a spike and nowhere else in the solar system did, unless we could pinpoint an exact cause, like something happened on Earth or something. So we could assume that most places in the solar system had a lot more impacts in the past than they do today. And we know today's by small impacts on the moon and Mars, and we also can basically count the number of things that could hit the various bodies in the inner solar system and how big of a crater they'd likely leave to get an idea of what the impact rate is today. So this is giving us a history, and this gives us a very important thing we're going to come back to when we get to solar system formation, which is this possibility that around a little under 4 billion years ago, there was a dramatic change in the impact. So this hypothesis was called the late heavy bombardment, or aka the lunar cataclysm. So the general theory is that solar system forms by accretion, which means a lot of bodies hitting one another, and that's not going to turn off as soon as you form the Earth and the Moon, or you finish forming the Earth and the Moon. So we always kind of expected a general decrease of the impacts. But their thought was that the rate of the decrease might have changed, that this lunar cataclysm was a clear either sudden increase and then decrease, or a change in the slope of the impact, and we don't really know why. There's lots of theories about why, but whether this happened and to what degree was the moon a special focus versus a general solar system trend. So pretty much if you see an age in the solar system that's not on the Earth or the Moon, it is based on crater counting, almost certainly. You do have to make, again, some assumption on how does the rate of crater formation on the Moon relate to Mars, relate to the outer solar system. And until we bring back a rock from a known place elsewhere in the solar system, we can't really check how good our models are. So this is one of the many, many reasons why the Mars folks would really like to get some Mars rocks from a place they know where the rocks came from. Martian meteorites can't help us here because we don't know where on Mars they came from beside, or even if that place has remained unchanged since the meteorite, was launched by an impact. So, all right, what do we talk about today? We talked about the phases of crater formation: contact, compression, excavation, collapse, and modification. That craters accumulate on all solid planetary surfaces and are cleared away by other geologic processes. And the moon is basically the linchpin of our timescale for the solar system, because we have both good crater counts over the entire moon, because the moon is full of craters, and we have rocks which we've determined absolute dates by radioactive dating, which we're going to cover later in the course.